The Neyman Pearson idea that we mentioned is a little more than just common sense. You have two types of errors, no question about that. Obviously, there has to be two types of error. And Neyman Pearson just says that first identify the type of error which is more serious, that is type 1, the other will be type 2, and then what you do is that you merely first try to control the probability of type 1 error, in the sense keep it below a certain pre-specified threshold, and subject to that condition try to minimize the probability of type 2 error. That's just common sense. But it is surprising that even this common sense technique may lead to a test which is quite absurd. And in order to rectify that, they introduce the next step in their paradigm. But first, let us take a look at one simple example where this common sense paradigm leads to an absurd test. So we shall consider a simple coin tossing setup. We have a coin and we want to know about the probability of head of that coin, and I am given this information that this probability of head is either 0.5 or 0.7. So the parameter space is not just 0 to 1, it is only 2 points. It's a double turn set. Either it is 0.5, the probability, or it is 0.7. I want to know which. So these are my two possibilities, and I will tell you that take the 0.5 value as your H0 and 0.7 as your H1. Of course, in a practical problem, you will have to think about the underlying story and hence figure out whether whether this error is bad or that error is bad, and accordingly decide which one should be H0 and H1. But in this toy example, I am just telling you which one you should take as H0 and which one you should take as your H1. So you need some data. What we do is that we toss this coin 6 times and look at the number of times we are getting head. So that can be either 0 or 1 or 2 or 3 or 4 or 5 or 6. Based on this, we want to decide whether probability of head is 0.5 or probability of head is 0.7. Since our sample space here is of size 7, the set 0 to 6, so our test is basically a function from this set to the double turn set accept reject. So that is our test. For every possible value of x, say x is the number of heads, I have to either say accept H0 or reject H0. So it's a function from the set 0, 1, 2 up to 6 to the set accept, reject. And we want to find one such which will have the following property. Number 1, its probability of type 1 error should be less than or equal to, say, 5%. I fix the threshold at 5%. And subject to that restriction, its probability of type 2 error should be minimal. So let us first start worrying about the type 1 error. So for that we have to think about only H0, that is the situation where the coin is unbiased. So for that, let us write down all the probabilities that we have for our different possible values of our data. So it can be either 0 or 1 or 2 or 3, 4, 5, 6, and I have written down the binomial probabilities under the situation when probability P is equal to 0.5. Now we have to pick a subset of these set 0, 1, 2, 3, 4, 5, 6 of all these values such that the probability of type 1 error remains less than 0.05. Now, what is probability of type 1 error? The probability of rejection when H0 is true. That is, let us first focus on the critical region. Critical region means that subset of the sample space for which we are going to reject the null hypothesis. So, let us pick that subset. Of course, picking that subset will uniquely specify our test, because you reject for this or you accept for the rest. Now, let us quickly understand, can I put this value 4 in my rejection set? Well, no, because if I do that, then I can see that the probability for that is already 0.20, something more than 0.05. So, if I put that, already my type 1 error will be more than even 20%, not just 5%. So, I cannot put 4 in that point. Can I put 0 in my set? Yes, that is possible because it is only 0.016. Can I put 1? No, I can't do that. Any probability which is more than 0.05, I cannot put. So, if I start thinking in this way, then I will have the following thing. First of all, I can have just the empty set. No one says that you have to reject. If you take the rejection set as empty set, this basically means you are always going to accept it, and that is also one possible valid set. And for this, probability of type 1 error will be just 0. Now, we can take only the set singleton 0, that is allowed. So, if you take only the set singleton 0, then probability of type 1 error will be just this number, 0.016. By the same argument, you can also take this extreme, which is the set singleton 6. Observe that if you add these two things, then the sum also remains less than 5%, which means you are quite well entitled to take as your set this doubleton set 5, 0, 6 and 0, 6. So, all these critical regions will lead to tests which satisfy the condition that probability of type 1 error is less than or equal to 5%. And these are the only 4 possible tests. So, Neyman Pearson's idea is to pick out of these 4 sets the test which will give you the least probability of type 2 error. So, these are the only 4 competitors. Now, let us see how we can do that minimization. We are trying to minimize the probability of type 2 error, that is, we are trying to minimize the probability of accepting the null hypothesis when the null hypothesis is actually false. Now, we are trying to minimize the probability of accepting, which means we are trying to maximize the probability of rejecting. It helps if we think always in terms of rejecting, because the 4 sets that we talked about are actually rejection regions. So, we want to pick that particular subset, those 4 things, empty, singleton 0, singleton 6 and doubleton 0, 6, for which the probability of rejection will be maximum under H1. Now, observe that these sets in this particular example, they have this one largest set. This doubleton 0, 6 is obviously the largest set. So, whatever may the alternative hypothesis be, it is clear that the probability of that set must be largest. So, probability of the doubleton 0, 6 must be greater than or equal to the probability of empty set, probability of singleton 0, probability of singleton 6. So, without any doubt, that particular set is going to win the race. So, our test now becomes reject the null hypothesis if and only if the number of heads that you observe is either 0 or 6. But is this natural? This isn't because, number one, I did not even have to take a look at what is that alternative hypothesis, whether it is 0.7 or 0.1 or 0.9, the argument that I gave remains equally applicable for all these things. And secondly, just look at the test. I say that if you get 0, that is, you out of 6 tosses, you get all tails, not a single head, then I am asking you to opt for H1. Now, in my case, H1 is probability of head is 0.7 and null hypothesis says probability of head is 0.5. 0.7 is more than 0.5. So, when there is no head at all, would you go for the probability of head higher or lower? Obviously, you should go for the lower probability of head, right? So, common sense says that if you get 0 heads, then you should go for the least possible value of probability of head, that is for H0. Yet here Neyman Pearson paradigm seems to say that you should do just the other thing. So this shows that even in this very simple case, a problem occurs with the very common sense technique of Neyman Pearson paradigm. And this is not a pathological example. You can modify this example in lots of different ways, still you will have this fundamental problem. To avoid this, Neyman and Pearson introduced a rather interesting trick. They say that instead of working with a test, which is a function from the sample space script x, to the doubleton set accept reject, which they encoded as 0 and 1. So 0 means accept H0 and 1 means reject H0. What you do is that you consider this range of the test as the closed interval 0, 1. So I can either accept 0, I can reject 1, or I can do something in between. Now what is meant by doing something in between? That is the new concept that Neyman Pearson introduced in order to avoid giving rise to weird tests. Such a test is called a randomized test, and the best way to understand a randomized test is to work through an example. So first consider this test. So again I am working with that situation where my sample space is the set 0, 1, etc. up to 6, and my test is phi. Now when I write phi 0 equal to 0, by this I mean if x is equal to 0, then you just accept H0. Similarly, if it is 1, x equal to 1, you get exactly 1 head, you will accept it. On the other extreme, if you have phi 6 equal to 1, which means if you get 6 heads, then you will reject your H0. 1 means reject. The interesting thing happens when you have this 0.5. What does it mean to say that if you get x equal to 3, then you half reject it? By this we mean the following. What you will do is, suppose you get x equal to 3. Now you take some coin with probability of head equal to 0.5, some other coin. Toss it independently of everything. If that coin shows head, in that case you will go for reject. If that coin shows tail, you will go for accept. So that is what is called a randomized rule. So when you do a randomized rule, remember that your final conclusion depends not only on the data but also on the extraneous randomization that you have introduced in the form of this coin toss. So now all these things may be numbers between 0 to 1. Now this naturally begs the question, what is then my definition of probability of type 1 and probability of type 2 error? They cease to be just sets, subsets of script x. Well, we define it in this way. Probability of type 1 error is nothing but expected value under h naught of phi. Just see that if my phi is purely 0 and 1, nothing else, that is an indicator function, then its expectation is simply the probability that it takes the value 1. So, if I take expectation of phi, that is basically means probability of rejection. Now, here this rejection is taken in a more general sense. Even if I am rejecting with some probability, I am taking that into account. So, probability of type 1 error is expectation of phi under h naught. Similarly, probability of type 2 error, which is probability of accepting, which means 1 minus rejecting. So, it is 1 minus expectation, the same expectation, but this time I am taking it under h1. So, Neyman Pearson modified their paradigm, or I might say updated their paradigm by saying that I will specify some upper bound for probability of type 1 error. You consider all those tests, possibly such randomized tests also, for which this quantity is less than or equal to that pre-specified bound. By the way, that pre-specified upper bound is called the level of the test, sometimes called the size of the test also. Subject to that, you try to minimize this probability. By the way, this quantity is also called the power of the test. So, it is same as maximizing the power. So, that was the updated Neyman Pearson paradigm, and interestingly, this solved the problem. So, if you work with this thing, you will never get those weird tests. Now, this might make the problem look like a much more complicated problem, because earlier, in our example at least, we had only finitely many tests that satisfied that probability of type 1 condition. But now there are uncountably infinitely many tests that we might consider when we are allowing randomization. So, it might seem that even to write down the general form of the test satisfying the first condition is very difficult, let alone trying to choose that test out of them which will minimize probability of type 2 error. But actually, mathematically, it is a much simpler problem. True, it is not a finite set anymore, but it is a very well structured set. If you think for a moment, you will see that the set of all tests, all randomized tests that we are considering, that is all the randomized tests that satisfies that probability of type 1 condition, though that is an uncountably infinite set, but it is a nice convex set. It's a convex set. If you take two tests and you take any convex combination of them, take average of the two tests, which now makes sense because I have reduced everything to just functions from a set to the closed unit interval. So, you can now meaningfully take convex combinations. You will see that that test also satisfies the same condition. So, now you have to optimize your probability of type 2 error over a nice convex set, and there are plenty of mathematical tools which will allow you to maximize or optimize a function over a convex set, and that is what Neyman and Pearson took advantage of, and they came up with a brilliant solution, a completely general analytical solution by which you can find that particular test which will indeed minimize probability of type 2 error or equivalently maximize power. The test that they proposed is famous as the Neyman Pearson lemma or Neyman Pearson theorem, and it goes like this. It says that the best test according to their criteria is unique, and not only that, it is given by the following very intuitive form. it says the following, that you will either accept 0 or reject 1, or you will do randomization. So all these things are allowed. So gamma is some number between 0 and 1. You will randomize according as you consider this thing. L1x says the probability or the likelihood of the data under H1. So in our discrete example, this simply means the probability of observing this value of x, whatever you have observed, if H1 is true. So if H1 means probability of head is actually 0.7, then what is the chance that you are going to observe this particular value of x? Divide that by the same probability but under H0. You take this ratio, this is the likelihood ratio. In this version, I have put that H1 thing on top and H0 thing on the bottom. And if this quantity is small, that is, you have less evidence in favor of L1 than in favor of L0, small means less than some C, in that case you will accept, which is very natural, because if you have less evidence for H1, then naturally you go for H0. Similarly, if you have more evidence, then you go for 1, and if you are exactly at that threshold, you are kind of undecided, then instead of going for either this or that, you will randomize, toss an additional coin and take your decision based on that. So this test is not yet completely specified. It involves two quantities to be specified. One is gamma and the other is C. Now these two things are to be obtained using the particular level that is given to you. That is, you are given some upper bound for probability of type 1 error. So when I said best, I mean best at that particular level. So using alpha, you can work out your gamma, you can work out your C, and those two things may be worked out uniquely. So we will see some examples and you will see why and how they may be worked out uniquely. So this test is the best possible according to that Neyman Pearson sense, and it is a meaningful test. Now I said best, the standard term is most powerful test. Most powerful because of the obvious reason, you have maximized power. Minimizing probability of type 2 error means same as maximizing power. So it is the most powerful test of that particular level. It is unique and it is given by this very intuitive structure. If evidence for H1 is more than evidence for H0, more means with respect to a certain threshold, then you take your most intuitive conclusion accordingly, and that is going to be the best. Now let's take a simple example. In our example that we had, so we had got these 0, 1, 2, 3, 4, 5, 6. I have plotted them in the horizontal axis and I am plotting the likelihood ratio here. So for example, if I take this value 5, what is the height here? The height here is you take probability of x equal to 5 when H1 is true, that is when p equal to 0.7, divide that by the same probability when p equal to 0.5. So I get a ratio and I have plotted them, and you can see since 0.7 is more than 0.5, as you go up, that is as the number of heads increase, your probabilities, the ratios are also increasing. So according to our Neyman Pearson paradigm, you will choose your rejection region starting from this end because the values are high. So you basically draw a horizontal line like this, that is your C. Things above will constitute the rejection region, things below will constitute the acceptance region, and if some dot happens to lie exactly on that line for that point, that is for that corresponding value of x, you are going to randomize. So in this case, if I look at this 6, I already know that the probability of that is less than 0.05, so I am going to reject for that. Come here, if I consider the probability of 5 under H0, so I am now thinking about that level condition, probability of type 1 condition, so I am thinking about probability of under H0 alone. You will remember that this was something which exceeds 0.05. So you look at how much you exceed. So you need only a part of that to attain your 0.05. So that part will determine what gamma you are taking. Suppose you need to take only half of this case. So in that case, you will take gamma equal to 0.5. You need 1/3 of the case only. So this probability plus 1/3 of this probability will give you 0.05. In that case, you take gamma equal to 1/3. And what is your C? Obviously, C will be precisely the height of this point. So you start growing your critical region from this, and every time you see whether you are exceeding that probability of type 1, if you find that you have still under probability of type 1, but if you take a little bit part of that for probability of this one, and then you will attain your level exactly, then that extra fraction will determine your gamma, and the height of this point will determine your C. So that is how Neyman Pearson lemma is to be used, and one might prove, not very difficult to prove, that this is the unique, most powerful test of that level.